Hi, in this video I'm going to be describing how to implement most of this paper here called Modeling Trees with a Space Colonization Algorithm in Blender using geometry nodes. In this paper, I'll leave a link to it so you can read through it, is an interesting paper that uses the 2005 space colonization algorithm, which was designed for making leaf venation, and updates it to being a 3D algorithm that can generate these tree shapes that you see right here. And the core algorithm is not so complicated, but it's also not trivial to implement in geometry nodes. And I've tried doing it a few different ways, and I think I've figured out what I think is the best way to do it in geometry nodes. And kind of an overview of the algorithm if you're not familiar with it. You start with a list of nodes and a list of attractors. And here these nodes are these black dots, and the attractors are these kind of blue-teal colored dots. The nodes here represent the branches of the tree, and the attractors represent just some abstract shape that you're trying to make the tree kind of grow into. So that one of the benefits of this algorithm is the branching is just sort of grown dynamically. You don't have to specify when you want to branch or how the branches kind of angle off the main trunk or anything like that. It's all just kind of an emergent property of the system. So the way that the algorithm works, you start off by having each of these attractors associate itself with the nearest node. Then it will check to make sure that each attractor is within a specified attraction distance of that node, and if it is, then it exerts an influence on these nodes here. Then you take the normalized direction toward each attractor and add them all together to get an average direction for each of these nodes that is influenced by the attractors. And then in that average direction, you then place a new node according to a specified segment length distance. And then once you've done that, you check each attractor to see if the nearest node is now within a specified kill radius. And if it is within the kill radius, then you remove that attractor. So you see here, there's only two left. Then you repeat the whole process all over again. These two associate themselves with the nearest nodes. Then you go back to step B, essentially. You can continue this until there are no attractors left, or just a set number of iterations until you're happy with it. That's the core idea of the algorithm. And now if we go into Blender, we can see I have a new Blender window right here. I'll just go into geometry nodes, and for now I'm just going to delete everything, and then we can figure out how we want to do this. And I recommend using a simulation zone, although I think you could also use a repeat zone probably. In our simulation zone, remember we needed a list of nodes and we needed a list of attractors. And then other than that, oh, sorry, this is not the right thing. I need to go into nodes here. So we need a list of nodes, and we need a list of attractors. And then in the group input here, I think I don't need this for now. And I'm going to have an attraction distance. And I'm going to also have a kill distance. And I will have a segment length. Then we can think about how we want our algorithm to work. First of all, I recommend basing this on a mesh extrude node, which will make things a little bit easier. And what that means is that our input to our nodes will have to be it will have to be vertices. So just for now, I'm going to convert this to oops, that's the wrong one. Points to mesh or to vertices here. I'm just going to start off with a single node at 0, 0, 0, just this vertex. And our attractors, this is where I'll go back in to view the window here. For now, we can keep this in 2D just to make it a little bit easier. I'm just going to distribute points on this grid right here. We can preview that. It looks a little bit better if you have kind of more of them. Okay. And now that we have all of our inputs set up, we need to do our first step, which is calculating the nearest node index for each attractor. So this is quite simple. We sample the nearest, and we get our index. So for each attractor, we're going to sample the nearest point here. I'm going to store this as a named attribute. Change that to an integer and call it nearest. Then I would like to store another named attribute, which will just be the position of the nearest. And again, we sample index here this time. And this can be a vector. This can be a vector. And we hook this up. We get our nearest position. And then finally, we will store the nearest or distance to nearest. And this is pretty easy too. We just get our distance from here to here. Make that an integer, a float. And now what we've done is calculated the distance to the nearest node for each attractor, and we have the index of that node. I know in the original algorithm, the paper, it said that you should kill all of the nodes after the first or after the next step, but I find it a little bit easier to do it right here. What we can do is just a delete geometry node. And I'll make this a little bit easier to visualize. We join these together. Isn't this showing up? Oh, because I have this delete geometry, that's right. So I'm deleting everything right now. What I want to do is when the distance to nearest is less than or equal to our kill distance, that's when we want to kill these nodes. I think in the original paper they assume that none of the nodes are actually close enough to be killed within the first step, but we're just kind of randomly generating nodes, so we can do that right now. And then this will just be run on every iteration. Then we are going to calculate within the attraction distance which nodes, which direction each node gets pulled to place the next thing. And so we're going to need some of these. What we'll do is take the nearest position, we'll subtract it from the position. And then this gets us our direction if we normalize it. So this is a normalized direction from the this is a normalized direction from each point to the attractor point. Then I'm going to only count them if they're within the attraction distance. So if this is less than or equal to the attraction distance, and we've already calculated the distance, so distance to nearest is less than or equal to the attraction distance. I'm just going to scale that. So if it's less than or equal to, then this counts as 1, otherwise it counts as 0. And then I'm going to accumulate a field here. I find this is the most performant way of doing this. So what we can do is do this based on the nearest point as the group ID. And what this will do is for each of the original nodes, it will calculate a total here. And then we can normalize this, which will sort of average out the distance. And then what we can do is kind of copy this. I find the best way, kind of most performant, is we actually just set the position of every attractor to this. There's one mistake here. We actually need an attraction distance, which for now I'll just set to 1. We can see what's going on here. We have all of our attractors. We're calculating the distance, we're normalizing that, and then we scale it if it's within the attraction distance or not. And you can see the effect of that. These are all of the points that are within the attraction distance. So let's set it to just some number like that for now. Then we accumulate the field. Right now we only have one node, so they're all going to be kind of the same. We set the position here to that value, and then that gets us our vector that points from the node to this normalized weighted, or not weighted, but average direction here. So now that we've done that, we can, I think it's going to be nice to store this. Oh yeah, I remember what I like to do here. So if I merge this by distance, then now we only have 1 point. So then when we copy this over to the nodes, we don't have to do it multiple times, we just have a single one, which will make everything much more performant. And now we can set the position again, or actually we should capture the current position. And then once we capture this position, then this becomes the offset vector that we need. And then we can set this to the nearest position. We can move them all here. So now they go back to that node. That makes it easy when we move over here. We get our geometry proximity. And we can say when the nearest point here is, the distance is less than some super small amount here, or we could just say equal to 0. I think that'll be good enough. Then we will extrude our mesh, set to vertices, and only the points where this distance is equal to 0 here. And the direction that will do it is we will sample the nearest, and then sample the index here. And set it to this captured position, which, if you remember, was the offset. And the direction that will do it is that right there, but then the segment length will be the scale, which I'll set to, say, 0.1, and then this should be 0.2. So now it's important that your kill distance needs to be less than your attraction distance, and it's better if it's more than your segment length. So now we can see that we've extruded this vertice and we've created this new edge here. I think if we run this, oh, something's wrong. Okay, I found a problem here. This should be flipped. I was going in the opposite direction. We want to have the position, the nearest position subtracted from the position. And now, when we run this, you see it has created this kind of branching structure right here. And right now it's just 2D. And the paper extends that to 3D, but one of the cool things in Blender is we kind of get that for free. Let me show you. If I just change these initial attractor points, say mesh to volume, and then distribute points in a volume, let's say like this right here. We can look at it from here. Let's make our density way higher. Then we can raise this up on the z-axis and put this here, and then run it. And we start to get something kind of like a tree already. So just by playing with these settings, in general, your kill distance is going to be your most important thing. If you set this to be a much lower value, then you'll get more small branches like this. And if you set this to be a higher value, then it'll be, let's up that to 1. It'll be kind of a more sparse tree shape here. And then, of course, there's a number of things we can do to post-process this. You can convert this, right now it's just a mesh line or a collection of mesh lines. You can convert it to a curve and then do a mesh to curve and kind of get a tree shape. You can capture some attributes here, like the number of children you have before. And I'll make another video talking about some other things you can do, but this is the core space colonization algorithm, and I think this is a pretty efficient way of running it in Blender. And I'll save the rest for the next video.